ここからいきます。Thermal properties of the free electron gas application of the Fermi-Dirac distribution. Thermal property of the free electron gas. In a gas of free and independent electrons, the one electron levels are specified by the wave vector k and spin quantum number s, with energies that are independent of s in the absence of a magnetic field. With energies, and given by equation 2.7, that is decorated epsilon of k equal h bar square k square divided by 2m. We first verify that the distribution function 2.49 is consistent with the ground state t equals 0 properties derived above. In the ground state, those and only those levels are occupied with decorated epsilon of k smaller than epsilon EF, which is Fermi energy. So the ground state distribution function must be fks equal 1 when decorated epsilon is smaller than Fermi energy, and equal to 0 if the decorated epsilon of k is larger than EF. On the other hand, as t go to 0, the limiting form of the Fermi-Dirac distribution 248 is limit t go to 0 fks is 1 for epsilon k smaller than mu and equal to 0 epsilon k larger than mu. For those to be consistent, it is necessary that mu chemical potential in the limit t go to 0 is Fermi energy. We shall see shortly that for metals, the chemical potential remains equal to the Fermi energy to a higher degree of precision, all the way up to room temperature. As a result, people frequently fail to make any distinction between the two when dealing with metals. This, however, can be dangerously misleading. In precise calculations, it is essential to keep track of the extent to which mu, the chemical potential, differs from its zero temperature value of Fermi energy. The most important single application of Fermi-Dirac statistics is the calculation of the electronic contribution to the constant volume specific heat of a metal. Cv is T over V partial S partial T, where V is constant, equal partial U partial T. And here U is large U divided by V. Yes, I don't know, is this right? Maybe this is right. This is more like Helmholtz energy is constant. This is U minus Ts. I think this comes from like df dt constant. I'm not sure. Is this right? df dt, or should I do this way? I don't know. Should I do this partial f partial t for constant volume equals 0? I'm not so sure. How come this equation, this equality holds? I'm not so sure. I think I have to go through thermodynamics. I think it's okay to put V outside. Yeah, if we put V outside, we have this equality. Del S del T at fixed volume equal U partial U partial T at fixed volume. Anyway, and another thing we should know is some how do you call this, some strange infinitesimal quantity which is not state variable, this one, equal T ds, something like this, right? And in some conditions, so this dq equal to du, I think. For more precise derivation, we have to go back to thermodynamics. In the independent electron approximation, the internal energy U is just the sum over one electron levels of decorated epsilon of K times the mean number of electrons in the level 22. As usual, the factor 2 reflects the fact that each K level can contain 2 electrons of opposite spin orientations. U is 2 times summation over K allowed K decorated epsilon of K times F, which is Fermi-Dirac distribution function of decorated epsilon of K. We have introduced Fermi function f of decorated K, a decorated epsilon, to emphasize that f of K depends on K only through the electronic energy decorated epsilon of K and this is a Fermi-Dirac distribution factor. F of decorated epsilon equal 1 over something something. If we divide both sides of 255 by volume V, then 229 permits us to write the energy density U equal capital U over V as lowercase u equal integral over dk divided by 4 pi cube epsilon k f epsilon k. If we divide both sides of 249 by v, then we can supplement 257 via equation for the electronic density n equal uppercase n over v, and use it to eliminate the chemical potential. N is integral over k divided by 4 pi cube f of decorated epsilon of k. In evaluating integrals like 257 and 258 of the form, in evaluating integral of over k divided by 4 pi cube large f of epsilon k, yes, one often exploits the fact that the integrand depends on k only through the electronic energy decorated epsilon equal h bar square k square divided by 2m. By evaluating integral in spherical coordinates and changing variables from k to epsilon, integral over k divided by 4 pi cube f of epsilon of k equal integral from 0 to infinity dk k square divided by pi square f of epsilon of k equal integral from minus infinity to infinity d epsilon g epsilon f epsilon. Here g epsilon is m divided by h bar square pi square square root 2 pi epsilon divided by h bar square for epsilon larger than 0 or 0 when epsilon is smaller than 0. Since the integral 259 is an evaluation of 1 over v summation over all k and s f epsilon of k, the form in 260 shows that g epsilon d epsilon equal 1 over v times the number of 1 electron levels in the energy range from decorated epsilon to decorated epsilon plus d decorated epsilon. For this reason, g of decorated epsilon is known as the density of levels per unit volume, or often simply as the density of levels. A dimensionally more transparent way of writing G is G of epsilon is 3/2 times n over divided by epsilon f times epsilon divided by epsilon f times to the power 1/2 for epsilon larger than 0 and 0 for epsilon smaller than 0, where epsilon f and kf are defined by the zero temperature equations. Okay, here only this is epsilon f, not mu, even for t larger than 0. This EF doesn't mean chemical potential, zero temperature limit of chemical potential, but this here it just means literally some value of energy defined by some equation we saw before, where epsilon f and kf are defined by the zero temperature equation 221 and 225. A quantity of particular numerical importance is a quantity of particular numerical importance is the density of levels. A quantity of particular numerical importance is the density of levels at the Fermi energy, which 261 and 63 give in either of the two equivalent form. G of epsilon f is mkf divided by h bar square pi square, or G of EF equal 3/2 n over epsilon f. Using this notation, we rewrite 255, 57, and 258 as small u is integration from minus infinity to plus infinity d epsilon g epsilon f of epsilon n equal integration from minus infinity to infinity d epsilon g epsilon f epsilon. We do this both for notational simplicity and we do this both for notational simplicity and because in this form the free electron approximation enters only through the particular evaluation 261 or 263. Okay. Of the density of levels G. We can define a density of levels via 262 in terms of which we can define a density of level via 262 in terms of which 266 and 267 remain valid for any set of non-interacting, that is independent electrons. 23. See chapter 8. Okay. Figure 2.3. The Fermi function f of epsilon equal 1 over exponential something plus 1 versus decorated epsilon for given mu. At t equals 0 and t equals 0.01 mu of order room temperature at typical metallic density. The two curves differ only a region of order kBt about U. I'm not sure if this graphs were drawn on scale. Maybe not. I think this, if this is 0.001 mu, no. Okay. So if this is 0.001 mu, no, it's not possible, because this is mu. So this is mu, and this is t. And no way that this t is 1/100th of mu. It is no way. So this is not drawn on scale. Okay. Sorry. Thus, we shall later be able to apply results deduced from 266 and 267 to considerably more sophisticated models of independent electrons in metals. In general, the integrals 266 and 267 have a rather complex structure. There is, however, why in general? I don't know why he said in general. In general. I don't know. Okay. The integral 266 and 267 have rather complex structure. There is, however, a simple systematic expansion that exploits the fact that at most all temperatures of interest in metals, T is much smaller than the Fermi temperature 233. In figure 2.3, the Fermi function f of epsilon is plotted at t equals 0 and at room temperature for typical metallic densities. kBt divided by mu is about 0.01. no KBT here is much larger than 0.01 mu. Evidently, F differs from its zero temperature form only in a small region about mu, of which a few of width, a few kBt. Thus, the way in which integrals of the form minus infinity to plus infinity h of epsilon f of epsilon d epsilon differ from their zero temperature value minus integration from minus infinity to ef h epsilon d epsilon will be thus the way in which integral of the form something differ from the zero temperature value will be entirely determined by the form of h epsilon near epsilon equal mu. If h of epsilon does not vary rapidly in the energy range of the order of kBt about mu, the temperature dependence of the integral should be given quite accurately by replacing h of epsilon by the first few terms in its Taylor expansion about epsilon equal mu. So this is the Taylor expansion. 268. This procedure is carried out in Appendix C. The result is a series of the form integration from minus infinity to plus infinity of h of epsilon f of epsilon d epsilon is integration from minus infinity to mu h of epsilon d epsilon, then summation over n from 1 to infinity kBt to the power of 2n an derivation of 2n minus 1 times with respect to the epsilon h epsilon. Then we evaluate whole thing or second term at epsilon equal mu, which is known as the Sommerfeld expansion. The an are dimensionless constants of the order of unity. The functions h one typically encounters have major variations on an energy scale of the order of mu, and generally dd epsilon n times applied on h of epsilon evaluated at epsilon equal mu is of the order of h of mu divided by mu to the power n. I don't know why, but I just accept. Okay, this is of the order of this. When this is the case, successive terms in the sum-manifold expansion are smaller than big O of kBt divided by mu square, which is of the order of 10 to the minus 4 at room temperature. Consequently, in actual calculations, only the first and very occasionally the second terms are retained in the sum. In 269, the explicit form for this is, we have to see appendix C for this. But anyway, let me see the footnote 24. The expansion is not always exact. Why not exact? But is highly reliable unless h of epsilon has a singularity very close to epsilon equal mu. For example, h is singular at epsilon equals 0, as in the free electron density of levels 2.3063, then the expansion will neglect terms of the order of exponential minus mu divided by kBt. I don't understand. For example, h is singular at epsilon equals 0, then the expansion will neglect terms of the order of exponential minus mu divided by kBt. Anyway, okay. Which are typically of order e to minus 100, which is about 10 to minus 43. See also problem 1. So this is the result. Oh my god. Integration from minus infinity to infinity of h of epsilon f of epsilon d of d epsilon equal integration from minus infinity to mu h of epsilon d of epsilon d epsilon plus pi square divided by 6 kBt square h prime derivative of h as a function of mu plus 7 times pi to the power 4th divided by 360 times kBt to the power 4. There is no second derivative. Then h, third derivative of h as a function of mu, then order of kBt divided by mu to the power 6. Anyway, when this is the case, successive terms in the Sommerfeld expansion are smaller than this is I think this smaller this one. I think this one. And the second term, very occasionally the second term is this one. Is that right? I don't know. Let me see. H mu divided by mu to the power n. Divided by mu. And this guy is h of mu divided by mu cube. Okay. I don't know if this is working. Is it working? Actually, that's okay. Okay. Then, to evaluate the specific, okay, now we change the subject. We want to evaluate the specific heat. Okay, we want to evaluate the specific heat now. To evaluate the specific heat of a metal at temperatures small compared with TF, we apply the Sommerfeld expansion 270 to the electronic energy and number densities, equation 266 and 267. So there we obtain U is something like this, integration from 0 to mu epsilon g epsilon d epsilon plus pi square over 6 kBt square, then mu g mu plus g mu plus order of T to 4. N is integration from 0 to mu g of epsilon d of epsilon plus pi square over 6 kBt square g prime mu plus O order t to the power 4th. Equation 272, as well as we shall presently see in detail. Equation 272 implies that mu differs from its t equals 0 value EF by terms of t squared. Okay, so because this whole thing should be 0 to epsilon f g epsilon d epsilon. So this and this are different by this value. Implies that mu differs from its t equals 0 value epsilon f by terms of order t squared. Thus, correctly, to order t squared, we may write integration from 0 to mu h of epsilon d epsilon equal 0 to epsilon ef h of epsilon d of epsilon plus y mu minus epsilon f h of, it's very confusing, h of epsilon y (22) implies that mu differs from its zero value by terms of t squared. I think this is okay. Okay, this has nothing to do with the second part. Okay, this first term can be written as this. We can actually, the second term on right hand side, this is some approximated expression for this and this. So we can just plug this in to the equation. If we apply this expansion to the integrals in okay, yeah, I don't understand the logic. No idea. No idea about the logic logic here. I don't have any idea about logic here. But anyway, this first term can be expanded to this as this. This is just a first order expansion near E equal EF. If we apply this expansion to the integral in 271 and 272 and replace mu by EF in the terms already of order 2t square in these quantities, where is the t? Okay, because this is here. This term is t square. That's why this part was replaced from mu to EF, right? And here too. G mu G. Where is the EF? Here is EF. And this mu is also replaced to EF. This mu, this is also replaced from mu. And of course this EF was also from mu. And we do the same for carrier density n. Integration from 0 to EF g epsilon d epsilon e minus mu minus EF. Then this g, this EF was replaced from mu plus pi square over 6 kbt square g prime. Here is g prime. This is g prime. I'm not sure. G. Okay, anyway. So this is from mu. This is also replaced from mu. Maybe it is too much. I think we can continue next time. So this is 46. Page 46. We finished up to page 46.